All right, let's work through the 3.6 class activities. We've developed a nice shortcut for solving a linear second order ODE that bypasses all the work of finding eigenvalues and eigenvectors. It works even if the characteristic polynomial has complex roots. So let's see an example of that. We're going to use lucky guess shortcut to find the solution to the second order ODE. So we start by making a guess of the form y equals e to the st, and we're going to use the method from the demo to solve for s. So y double prime would be s squared e to the st plus 4 times y prime, which is se to the st, plus 13y, which is e to the st. We want to set that equal to 0 and solve. So I factor out e to the st, and I have s squared plus 4s plus 13. E to the st is never 0, so I just have to set this quadratic equal to 0. It doesn't factor, so I'm going to use the quadratic formula. So negative 4 plus or minus the square root of b squared, which is 16, minus 4 times a times c all over 2a. All right, so 16 minus 52 is negative 36. Oh, that's nice. Nice perfect square. Okay, so I have negative 4 plus or minus 6i over 2. And that simplifies to negative 2 plus or minus 3i. So I have two complex eigenvalues. So if you remember, last time we dealt with complex eigenvalues when we were dealing with a system of equations, we said just take one of them, and that's all you need. So I'm going to take one of these complex eigenvalues. I'll use the one with the plus. It's a little easier. And plug it into y equals e to the st. So we have y equals e. S is negative 2 plus 3i. T. We distribute the t to both terms, and our solution will look like y equals e to the negative 2t plus I 3t. Okay, and then I'm going to use rules of exponents to rewrite it like this. Y equals e to the negative 2t times e to the I 3t. De Moivre's theorem to rewrite it as, I'm just copying e to the negative 2t part, and then e to the I 3t I'm going to rewrite as cosine 3t plus I sine 3t. Distribute my e to the negative 2t, and I get e to the negative 2t cosine 3t, which is real, plus I times e to the negative 2t sine 3t, which is imaginary. So this is y real, this is y imaginary, and the general solution is a linear combination of those. So I have k1 e to the negative 2t cosine 3t plus k2 e to the negative 2t sine 3t. Okay, so what happens if we use lucky guess in a general case? So my guess is always e to the st, right? So y equals e to the st. So I'm going to have a times s squared e to the st plus b times s e to the st plus c e to the st equals 0. We're going to factor out an e to the st, and you're left with as squared plus bs plus c. And this is a quadratic equation. As squared plus bs plus c, you just use the quadratic formula. So a, b, and c, the coefficients on y double prime, and y, end up as the coefficients on s squared, s, and the constant term in the quadratic. So we don't have to go through this whole show of guessing y equals e to the st and plugging in. You can just jump to writing down the characteristic equation. It's always going to be as squared plus bs plus c. Okay, so now that we have our shortcut in hand, we're going to use it to study the equation that models the harmonic oscillator in a little more depth. So if we have an undamped harmonic oscillator, that means that there is no middle term, no by prime term. Its characteristic equation is going to be ms squared plus k. There's no s term in the characteristic equation because there's no y prime term in the harmonic oscillator. So I set that equal to 0 and I solve for s. So I get s squared equals negative k over m, which means that s is plus or minus the square root of k over m I. Because remember, k and m are both positive, so we're taking the square root of a negative, which brings in an I. So this is a complex eigenvalue. The real part is 0, which means the fixed point is a center. So we have periodic solutions. We have a phase portrait that looks like circles or a center, and then our solutions at y of t and v of t are sinusoidal. So this is perpetual motion. There's no damping, so the mass on the spring just moves back and forth forever. Okay, so if we have damping, then the characteristic equation is ms squared plus bs plus k equals 0. And when I use the quadratic formula on that, I get s equals negative b plus or minus the square root of b squared minus 4 times a times c, using m and k for a and c this time, all over 2a. All right, so the value under the square root, this b squared minus 4mk, that's going to affect the type of equilibrium point at the origin. So if that value is negative, then we are taking the square root of a negative number. We're going to have complex eigenvalues, which means we're going to have some kind of spiral. The real part is negative, which means this is going to be a spiral sink. Okay, if b squared minus 4km is positive, we're taking the square root of a positive number, which means this is not complex, which means it's either a sink, a source, or a saddle. Sink, a source, or a saddle. And it all depends on the signs of the eigenvalues. So if I have b squared minus 4km, how would that compare the square root of that? I want to compare that to the value of b. Okay, so b squared minus a positive value means that what's under here is a little bit smaller than b squared, which means when I square root it, it's going to be a little bit smaller than b. So if I have negative b plus something smaller than b, this is going to be negative, less than 0. Okay, so I have one eigenvalue that's negative, and then if I do the minus, negative b minus a positive value, any positive value, whatever that square root comes out to, this is also going to be negative. So I have two negative eigenvalues, which means that this is a sink. two real, both negative eigenvalues gives a sinc. And then critically damped happens when b squared minus 4km equals 0, so we only have one eigenvalue, negative b over 2m. Oh, a rough representative phase portrait. Okay, so a spiral sinc looks like this, spiraling in. The swirl direction you would determine based on the problem. And then a sinc typically has two straight line solutions that point in. And the solutions start out parallel to one and tangent to the other, and come in tangent to the other. So the way you determine which is which is they start out parallel to the eigenvalue that is further from 0 and come in tangent to the eigenvalue that's closer to 0. So it would look something like that. That's what a sinc looks like. And then critically damped, when you have only one repeated eigenvalue, you have only one straight line solution. My one eigenvalue is negative, so I have pointing towards the origin. And then solutions are going to come in tangent to one side and end up parallel to the other. Something like that. So this summary is going to be super helpful when you're working through these kinds of problems. So make sure you read it and refer to it as needed.